Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show CFD heat transfer analysis through a special type of tank that will be used as a surface condenser used in power plants. So this tank will be having water at a temperature of 100 degrees centigrade, and at the exit we'll get temperature at a desired level. For understanding the geometry, let us have a segmented view of this model. This is a special type of tank actually. We're cutting this model from front plane. You can see that the bottom part, the 50% of this one is filled up with water at a temperature of 100 degrees centigrade, and it is containing two different types of shells. This is the top shell, and from this top shell we are providing water at a normal temperature and high pressure, and that will be injected through these nozzles. It is having specific numbers of nozzles surrounding this inner shell up to an angle of 120 degree, right? And from these nozzles we will provide normal temperature water at a high pressure, and that will be injected through this nozzle inside this tank. And the tank is already having water at a temperature of 100 degrees centigrade. The bottom part of this tank is filled up with water, and the top part is filled up with air. When we will inject water from this nozzle, so some kind of misting effect of water will happen inside, and ultimately it will be mixed with the water down level. So whenever some excess amount of water is coming inside this tank, so the level of water will be increased, and at the same time mixing of water at different temperatures will happen, and as the level of water increases it will come out from these openings. We are having specific numbers of openings. As the level of water increases it will come out from this opening, and it will be accumulated at the bottom part, and it will be collected at the bottom openings. So in this case our aim will be to have not only an analysis, but at the same time we'll go for some kind of parametric study and also optimization. Optimization is equal to get that water temperature at the exit level as per our requirement. Okay, we are having single fluid domain, and in a single fluid domain two heterogeneous fluid cannot be mixed, so we are utilizing special method known as free surface technique using SolidWorks flow simulation, right? So without wasting time, let us start our simulation. And also you can see one thing, that when we are injecting water at a high pressure through these nozzles, only the nozzles will be acting as a one-way valve. It cannot pass from inside to outside. Only water will be passing from outside to inside. For understanding this one in better way, we can have a segmented view from different plane also. Let us cut it from right plane. You can see that geometry. See, water is coming out from this opening from the nozzles. It will be coming down and it will be mixed in the water, and water in the downside is having a temperature of 100 degrees centigrade. It will be mixed with the water at 100 degrees centigrade, and by the same time the level of water will increase, so water will come down from these openings. And in this case one special thing is there, the temperature of water at the bottom surface will not come down that much. It will be almost 100 degrees centigrade throughout this analysis. Only the thing is there will be mixing of water from this one at the top surface only. So we have decided to have three different goals. One goal will be to have temperature at the top surface of this water. Another goal will be to have temperature at the exit surfaces, and also we have created one kind of dummy surface here to see the misting effect, because at the dummy surface whenever water will be coming out from these nozzles there will be some kind of water misting effect. To see that water misting effect, we have created one dummy surface, and at that surface we will try to get average temperature of fluid. So three different goals we are determining, right? So without wasting time, let us start our simulation, and it will be started with flow simulation. And the flow simulation environment will be created with the wizard itself. We are keeping the name of the project as project 4 because three different projects we have already started before. Next to that we need to select unit system. We were considering SI unit system, and from temperature we will select degree Celsius, Next to that, it will be an internal analysis, and from physical features it will be fluid flow, connection, and as it is a free surface technique, it will be a time dependent transient analysis. And we can see total time for this analysis equal to 2 seconds, and we are considering output time step equal to 0.01 second. After each 0.01 second, we'll save the results. We need to depend on gravity also, and the direction of gravity is indicated by y. So along y it will be minus 9.81 meter per second square, and along z it will be 0. As I told, in this case it will be heterogeneous mixing of water and air, so we need to depend on free surface technique. Next to that, we need to select gases or fluids. We're considering air as default fluid, which will be prevailing inside this tank from the beginning itself, and liquid it will be water. Two different fluids, water and air, we have considered. Next to that, container we're considering made up of stainless steel 321. Next to that, default out of all thermal conditions and roughness we're considering. And finally, thermodynamic parameters, pressure will be 1G to 135 Pascal, and temperature it will be 20 degrees centigrade. And initial concentration it will be filled up with air, and solid parameters also it will be having temperature of 20 degrees centigrade. Let us finish this. You can see this is the computational domain, right? We can hide it. Let us have a segmented view of this model. We can cut it from front end. Now first of all, we need to apply our initial conditions. That means the solid part what we have made during modeling in the bottom part of this inner shell, that should be disabled and that to be converted as water at a temperature of 100 degrees centigrade, right? So conditions, initial condition, and we need to select this solid at the innermost shell. That can be selected from the geometry itself. So we have selected that solid component, that to be disabled as solid, and that to be converted as water at a temperature of 100 degrees centigrade. Done. So the solid part inside this inner shell, we have disabled that solid and considered this one as water at a temperature of 100 degrees centigrade at a pressure of normal pressure 10135 Pascal. Go and check. Done. Next to that, you have to provide some kind of boundary conditions. So boundary conditions, insert boundary condition, we need to provide mass flow rate from these openings or from these nozzles. We can provide mass flow rate from these openings, or same way you can do it from this surface also. Let us provide inlet mass flow rate as 0.001 kg per second, and that will be passing from this top surface of this inner shell. From this inner shell, at the top surface of these nozzles, we are providing water at a temperature of 20 degrees centigrade and at a higher pressure at a rate of 0.001 kg per second. Let us see thermodynamic parameters. It will be having pressure of 251,325 Pascal. It is almost 2.5 times higher compared to the normal pressure, and temperature will be 20 degrees centigrade. At normal temperature and high pressure, we are injecting water from this surface, right? And substance concentration, let us say it will be water. Go and check. Done. So one boundary condition we have already applied. Next to that, we need to provide some kind of other boundary conditions, that means atmospheric pressure at the exit locations. We are having a lot of openings, and at these openings you have to provide atmospheric pressure as a boundary condition. So boundary conditions, insert boundary condition, and it will be environmental pressure at the exit locations. Let us select those locations. Go and check. So we have provided atmospheric pressure at the exit locations. Next to that, we need to have some other boundary conditions. From the walls, we'll be having some kind of convectional heat transfer. So it will be heat transfer through convection. So we need to select those walls. So boundary conditions, insert boundary conditions. It will be walls, and we need to provide specific convective heat transfer rate from specific locations. Let us provide from this inner surface. Heat transfer will take place at a rate of 10 watt per meter square degree Kelvin. Go and check. And again from the other surface, that means from the top surface here itself, heat transfer will take place again with a different convective heat transfer coefficient. So boundary conditions, insert boundary conditions, walls, and from top surface it will be having convective heat transfer coefficient as 5 watt per meter square degree Kelvin from this top surface, right? You can select this portion also. Done. Let us see the previous one again. Convective heat transfer coefficient, edit definition. We need to select this location also. So from inside, convective heat transfer coefficient we are providing at a rate of 10 watt per meter square degree Kelvin, and from outside at a rate of 5 watt per meter square degree Kelvin. So all the boundary conditions we have applied. Next to that, we need to select some goals. We need to have 3 different types of goals. That means temperature at the exit surface, temperature at the top water level surface, and also temperature at some dummy space, right? And while performing this simulation, the dummy space should be disabled, right? So goals, insert surface goals. We need to have average temperature fluid at the exit surface. Let us select the exit surfaces first. Selected. We're going to create a single goal for all these exit locations. Green check. That is average temperature fluid at exit surface, right? You can rename this one as average temperature fluid at exit. Done. Next one, we have to have some other goals. That means average temperature fluid at the top water surface. So it is a special type of surface condenser. You can see that at the end of this simulation, always temperature at the water surface level will be 100 degrees centigrade. Another goals, insert surface goals, and let us take the top surface of water here itself, and you can select average temperature fluid at top water surface. Green check, and we can rename this one as done. And finally, we need to have surface goal at the dummy space, and that dummy space will show actually the misting effect of water, that at that level temperature of water will come down, right? So goals, insert surface goals. We want to locate that dummy space. This is the dummy space. Or we can do one thing to indicate this one in a better way. Let us have a segmented view from different plane. We can cut it from right plane and let us show the dummy space, right? This is the dummy space. So when water will be coming from these nozzles inside this inner shell, misting effect of water will happen and temperature of water will come down from 20 degrees centigrade to lower temperature. So goals, insert surface goal, and you want to have average temperature fluid at the dummy space. Let us select the dummy space. This is the dummy surface, selected, grain check, and we can rename this one as average temperature of fluid at dummy space. We have determined all the goals. Next to that, we need to run it, and before running we can go for some kind of meshing. Let us mesh it inside global mesh, and let us go for manual meshing, and let us check refinement level, and refinement level is up to 1. Let us increase this refinement level up to 4. Run check. And before running this simulation we need to do something else, like from solve we need to select calculation control options. We are running this one for 2 seconds, and from saving we can select periodic, and from here we can select parameters like immiscible air, immiscible water, volume fraction of air, and volume fraction of water. Done. Next to that we can run it. We have already done this one. Because for simulation of this one it will take some time. To save the time, let us see the results with the same input data that will be obtained from project number 3. Let us go back to project 3 and we can load the results. Results are loaded, and to see the dynamics of flow particles inside this container, let us make the model completely transparent. A model is completely transparent. We can view the dynamics of flow particles in a better way from this one, right? First of all, we want to see cut plots. Insert cut plots, and we want to see temperature of fluid from front plane. Grain check. It is showing temperature fluid through this surface condenser, and to view this one in a better way, let us import that transient explorer also. That is, from there we can see the dynamics of this flow pattern in a different way at different times, right? Because we have run this simulation for 2 seconds. Let us run it. Initially temperature inside this tank was 100 degrees centigrade, and you can see as time is approaching how water level inside this tank is increasing, and as it is increasing it will be coming out from these openings. These are the openings you can see, and higher temperature at these locations. And by the same time you can see some kind of blue zone is there. That zone is having lower temperature. So at this location we can see some kind of misting effect is happening. That one will show it from the goal plots, right? You can see how this is happening. You can see it from different plane also. Let us close it, and we want to see it from right plane. So cut plot, clear and hide, and we want to see from different plane, right? Cut plot, edit definition, we want to see it from right plane. Done. Now we can change the orientation to see it from right plane. See, let us run it from transient explorer, right? Initially temperature inside this shell was 100 degrees centigrade, and you can see different zones of water and air. And to see the misting effect, we can see here temperature range is in the range of blue zone, which is less than 20 degrees centigrade, right? We'll see all these things in a better way from the gold process itself. Let us clear and hide this one. So let us stop it, and instead of this one you can see pressure also. Pressure it will not be changing that much of, that is not that much important. Some other parameters also can be viewed. You can see immiscible water also. Let us see. This is the water level. It is increasing. Some kind of turbulence is there inside the level of water. You can see it from front side also. Let us view different things like surface temperature also. So we can view surface plots from here. Cut plot 4, clear and hide, and we're going to see it from different plane, right? Let us see surface plots. Insert surface plots, and we're going to see through all surfaces, and it will be temperature of fluid. Go ahead and check. Let us view it from different planes, right? You can see surface temperature is almost constant. It is not changing that much. Only at the exit level temperature is little bit of different. You can see it is indicated by this red color, and at the other surfaces you can see temperature is almost constant, right? Let us clear and hide this one. Next to that, we want to see some dynamics of flow particles. We've already created some before. Let us see dynamics of flow particles, right? So transient explorer, we can make it off, and you can do one thing. From results you can go for dynamics of flow particles or flow trajectories. Area definition. From all these surfaces we want to see dynamics of flow particles. Different surfaces we have selected. Let us see it. How the flow particles will be occurring inside this tank. You can view it in a better way. Let us view it from front end. Let us play. So in this simulation, one very important thing can be viewed, that is the temperature at the top surface of water. It will not be reduced that much. Always it will be having the temperature in the range of 100 degrees centigrade approximately, and at the exit level we can have a different temperature based on different input values of mass flow rate. So that one we'll see during our parametric study, right? And we can have desired level of temperature at the exit surface by optimization. That one also will show in our analysis, right? Let us clear and hide this one. Next to that, we want to see the most important part, that is our goals. That can be viewed from goal plots. Insert goal plots. You can select all the goals, and that goals can be transferred to Excel. So we are exporting this one to Excel and view it in a better way. These are the parameters. First one is average temperature fluid at dummy surface. From this one we can understand the misting effect of water. We have provided water from outside at a temperature of 20 degrees centigrade and at a high pressure of 2.5 times compared to normal atmospheric pressure. So initially temperature at the dummy space was approximately 6.056 degrees centigrade, and after 387 numbers of iterations you can see temperature at the dummy space is 2.35 degrees centigrade. So that means we can see huge amount of reduction in temperature at the dummy space. Definitely they was having some kind of water misting effect, right? because we have provided water from the nozzle at a temperature of 20 degrees centigrade, and at that specific dummy space we can see the temperature is 2.35 degrees centigrade. Next one is actually average temperature fluid at the top surface of water. So we can see after 387 numbers of iterations, we can see average temperature fluid at the top water surface is 99.99 degrees centigrade. That means there is very little amount of decrease in temperature of water level. So it is almost constant. It is almost approximately equal to 100 degrees centigrade. There is not that much of change in temperature of water at the top surface inside this inner shell, right? Or sometimes temperature was increased. So at 55 numbers of iterations, we can see the temperature was in the range of 100.03 degrees centigrade. And finally, after 387 numbers of iterations, we can see the temperature is in the range of 99.99649189 degrees centigrade. That is approximately equal to 100 degrees centigrade. Next one, you can see average temperature fluid at the exit surface. This is the most important part. You see average temperature water at exit surface after 387 numbers of iterations, it is equal to 57.311 degrees centigrade. So there is huge amount of increase in temperature of water. We have provided water at a temperature of 20 degrees centigrade, but here we can see the temperature of water at 57.31 degrees centigrade. That means there is huge amount of increase in temperature, right? But temperature of water at the top surface of water is not decreasing that much, right? Let us close it. So next to that, we can go for some kind of parametric study. In parametric study, what we have done is we have changed the different mass flow rate and see how the temperature at the exit surface and also temperature at the dummy surface is changing. Let us see the parametric study. We have already done this one, design of experiments and optimization. Let us see what we did. Let us see the scenario. From parametric study, we have provided different mass flow rates of water from the nozzles. We have changed the mass flow rate from 0.005 kg per second to 0.05 kg per second, and we have taken 5 different sets of readings. And you can see when the mass flow rate of water is increasing, that temperature at the exit surface is also decreasing, right? So when mass flow rate of water was 0.005 kg per second, in that case you can see average temperature fluid at exit is 50.27193 degrees centigrade, and average temperature fluid at the top water surface is 100.027766 degrees centigrade, and average temperature fluid at the dummy surface is 11.0548645 degrees centigrade. In experiment number 2, when the mass flow rate of water was 0.008 kg per second, in that case you can see average temperature fluid at exit is 44.587 degrees centigrade, and that at the top water surface is 100.036 degrees centigrade, and at the dummy surface it is 2.233 degrees centigrade. In experiment number 3, when the mass flow rate of water is 0.01 kg per second, in that case you can see average temperature fluid at exit is 44.9651 degrees centigrade, and that at the top water surface is 100.0342 degrees centigrade, and at the dummy surface it is 3.153 degrees centigrade. In experiment number 4, when the mass flow rate is more, it is 0.02 kg per second. In that case you can see there is some reduction in temperature at the exit surface, and we can see temperature of fluid at exit surface is 36.593 degrees centigrade, and at the top surface of water is still 100 degrees centigrade. It is 100.036 degrees centigrade. At the dummy space, we can see the misting effect in a better way. At the dummy surface, temperature is minus 3.7203 degrees centigrade. And in experiment number 5, when the mass flow rate of water is 0.05 kg per second, in that case you can see the average temperature fluid at exit surface is 28.9843 degrees centigrade, and again average temperature fluid at the top water surface is 100.0367 degrees centigrade. In all cases, temperature of water at the top surface is not changing. It is almost constant. It is almost 100 degrees centigrade, and what is changing is temperature at the exit surface is also changing, but by the same time temperature at the dummy space is also changing. In experiment number 5, we can see temperature at the dummy space is actually minus 3.5089 degrees centigrade. Right, so from this data we can see that if you want to get temperature at the exit level as per our requirement, we can have some idea from this data. Suppose you want to get the temperature at the exit surface to be 30 degrees centigrade. right? So which one will be better? In that case, our mass flow rate should be in the range of 0.02 kg per second to 0.05 kg per second. So this will be the range. Within this range, you can have temperature at the exit surface to be 30 degrees centigrade. Based on that, we have already performed one optimization goal, and let us see what it is. Let us see the goal optimization. So what we have done is we have changed the mass flow rate from 0.025 kg per second to 0.04 kg per second. Let us see the results from here, from the scenario. So it has already undergone 4 different set of readings with a specific range, and we can see finally at a design point number 4, when the mass flow rate of water is in the range of 0.039703721 kg per second. In that case, you can see average temperature of fluid at exit surface is equal to 30.19 degrees centigrade, and our targeted value was 30 degrees centigrade. So we could achieve the target with a discrepancy of 0.19 degrees centigrade, right? So finally, you can see that average temperature at the exit surface is 30.19 degrees centigrade when the mass flow rate of water is 0.0397 kg per second, right? So with this data, whatever temperature we want at the exit surface, that can be achieved through this design of experience and optimization, and finally through goal optimization. Okay, so with this one we'll conclude our today's analysis. This was a very simple analysis. This is a special type of surface condenser used in power plants. Actually, in power plants we are having water at a high temperature, that is wastewater. That water can be utilized for further feeding into the boiler through the surface condenser. This is a special type of surface condenser. Okay, so thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.